And then, like I said, namely the deletion of information that is stored in the quantum processes. These are things that happen inside of quantum computation. Let's talk about the history of quantum computing. This has been kind of relevant for me and relevant for us, and too, because on Wednesdays we are doing our quantum computing discussion series. Now, we've, of course, with my break that's happened and with some other things that got in the way of that, I did a lot of interviews and stuff towards the end of April and beginning of May, and those things will definitely put a little bit they put a little bump in our discussion series roll, but we're going to continue today and keep going on Wednesdays. And it's always good, I guess, for me personally, and I will project that thought onto every one of you, that I get to understand some history behind the topic that I'm studying. So right now, I am very much deep into quantum computing studying. My personal research is on relativistic quantum information inside of a quantum computer, more or less, which is a very new field. And it turns out to be very pertinent to a lot of new methods for solving quantum mechanical systems inside of quantum computers. So, of course, having some interest in this, it helps to know some of the history of what's going on. And there was a famous conference, but there's a lot of stuff that led up to the conference that I think is worth discussing. So let's discuss some of the things that happened in the mid-1900s that led up to that. Led up to that conference, and then what happened at the conference and what's going on more now. Oh, awesome, Phenomenauticus. That's cool. Yeah, hopefully this helps to some degree. All right, I'm going to try to shift some things around a little bit. Cool. That works. Beautiful. I can put that back there. All right. So, let's talk about quantum computing. Now, quantum mechanics turned to information theory in the 1970s. And this was the work that I was talking about a little bit earlier. Some of the interesting things that went on in the 60s and 70s by many famous physicists were people were interested about trying to figure out the biological structure quantum mechanically and basically quantum consciousness, really. But as well as some other quantum processes that might happen out in nature. So this idea of having, I guess I should say that there was a twofold thing going on here. The first one was that they wanted to figure out what the quantum mechanics systems were like in biology, in the human brain and other things, but also a computational version of that as well, right? Like there was, there was this mentality that the brain processes things computationally, and that needed a lot of work in the 60s and 70s. So that's what physicists turned to. Quantum mechanics, the people who were at the forefront of doing new quantum theory things, were interested in information theory in the 1970s. The Shannon information theory was something that had came out earlier, and this sparked a lot of people to think about that quantum mechanically. Some of the things that happened were by people like Bennett in 1973, who published a paper on reversibility, which we talked before about classical computation. And a lot of these things that we're going to be talking about in this history lessons are going to be callbacks to earlier discussion series episodes that we had. And if you'd like to go back and take a look at those, again, we're going over quantum computing on Wednesdays, and all the earlier episodes are on the YouTubers in the playlist titled Quantum Computation. I think there's 7 or 8 videos now. I lost track, but either way, and we're shortening them up too. So the beginning few might be longer, but these are the next ones here on out are going to be shorter. If that's something you're interested in. But Bennett did work on reversibility, which of course classical computation does not have a lot of reversibility. Holovo, in 1973 on storage of quantum information. Now remember, like, we kind of take it for granted a little bit, and like ooh and ah at the weirdness that is quantum information storage, right? Or maybe I should say the lack thereof of quantum information storage, where we know that quantum information gets basically erased upon measurement, that the information that goes through from gate to gate, from quantum gate to quantum gate, the processes that take place basically get erased upon measurement, right? There's no way to tap into that information before a measurement. Once the measurement happens, we're left with classical bits, right? Albeit, the method from getting those classical bits is all quantum mechanical, but after a measurement, you get ones or zeros. That's it. Or I should say ones or zero states, because they're qubits. But nevertheless, so, that was 1973, and then Roman Stanislaw Ingarden in 1976 on attempts to make Shannon's information theory applicable in quantum mechanics. So this was like one of the first and very successful attempts, I would say. It was successful in that I didn't actually read the paper, but it was successful in that it got a lot of people talking about this and a lot of people interested in this, and really kind of laid the groundwork for uniting these computational and quantum mechanics fields together. The larger attempt was going on. They wanted to relate humanity and living beings with computers and quantum processes. That's what I was talking about earlier. They had these goals in mind to understand how ideas happened quantum mechanically. QIT is probably the most plausible way to explain consciousness. I agree, Evolazzi. I personally agree. And this was the idea in the 70s and 60s that they agreed to, and they were interested in that highly. I don't remember the name of the author on the paper, but one very, very seminal paper. Hopefully, if I don't find it later, I can come back to it after the discussion and talk about who that was. But there's a very, very, very influential paper from a biophysicist about that very thing, and showed the limitations of treating the human or treating a bio something or other. We'll just say a human brain as a classical computer. All right, so let's see here. Okay, so then I guess we could enter with Paul Benioff. Benioff was born in May 1st. He is 1930. He was a PhD in nuclear chemistry, which, is what it is. But the idea is that in nuclear chemistry, he was able to work on quantum information and quantum computing. That was his main work, was quantum information and quantum computing, and he ended up working mainly at, believe it or not, Argonne National Lab for almost the entirety of his life, and he retired, I think, in 1995. This is going off memory, and still works there today, I believe. And Paul Benioff in 1980, though, so this was shortly after all of these papers were coming out, these ideas were coming out, lays down the first attempt at a quantum mechanical Turing machine, namely using the Schrödinger equation. Turing machines are like series of logical events, or series of logical operations, maybe is the better word. And Benioff laid down those a new series of logical operations, I guess I want to say, using the Schrödinger equation. He had some interesting things that he found. Oh, let me link you that paper, by the way, too. This was Paul Benioff's paper that I found. I think people have access to it. Maybe y'all do. Hopefully you do. But nevertheless, he recognized a few very interesting things. And remember, this was 40 plus years ago. This was in 1980. This was 40 years ago. And he recognized things that still haunt people today who work on this. Namely that error correction via dissipation would be a difficult problem. He wrote down the laws. He recognized that there was no heat dissipation. But then he also says, deep within the paper, that there will be heat dissipation. In a real situation, in a real computer, there will be heat dissipation. And that's a huge problem for classical computers during the 1970s and 80s. And this would be something that he recognizes would continue on in a quantum computer. But more so, he also recognizes that measuring is a different process, and it has a different outcome than just a quantum computation. Whereas in a classical computer, oh, thank you, Justin. Excellent. I didn't know that existed, but thank you. All right, so where were we? Oh, yeah, so we recognized that measuring was a different process and had a different outcome. And then, like I said, namely the deletion of information that is stored in the quantum processes. These are things that happen inside of quantum computation. We have a series of quantum gates. We run information through those gates. We entangle the information, kind of like smearing it out amongst the gates. And then at the end, we take a measurement, and all of that collapses to a single classical bit of information. And of course, we model it as a qubit because it is a quantum bit of information. But that is not to be confused in that they are. We should just say that the qubit could be treated classically after a measurement. That's probably the best way to say it. But the measurement problem is still a problem. It has been a problem. It's been a problem ever since the inception of quantum mechanics. And let's just talk briefly about why it's a problem. The measurement problem is basically what happens to quantum information after a measurement. Now, like I said, the measurement is pretty much just smeared out, or the information is pretty much just smeared out. And then after the measurement, we get a single result back for each process. So the way that you actually would do a quantum computation, if anybody's interested in why we know that it's going to work despite the fact that the information is still probabilistic, is that after you carry out 10,000 iterations of this experiment, you'll have a probability curve of outcomes, and you'll be able to determine it is a definite probabilistic outcome. So after 10,000, 100,000 iterations of these calculations, you can figure out what the probability distribution is going to look like. So what happens to that quantum information is the measurement problem. And there's three interpretations. We talk about the Copenhagen interpretation, which is basically that the laws of nature are probabilistic, and that there's really nothing to learn about the physical state before the measurement. But it's actually means something a bit deeper when you say it like that too. Like, it's not just like saying like, okay, like, we can't know anything because the math doesn't tell us anything physical. But it's actually like a legit stand to take on physics. Another way people might talk about the Copenhagen interpretation is that the spin is actually spinning up and down at the same time, I guess. That one's a little bit harder for me to wrap my brain around, but that's another thing that people might say. And they will certainly use words to say it that way, is that the particle is spinning up and also spinning down, whatever that means physically, but it is doing that before the measurement. And that one, like I said, is a little bit harder for me to swallow, but some people do talk like that and believe that that is exactly what the Copenhagen interpretation is telling us. The second interpretation is the Everettian interpretation. That's one where there is one wave equation of the entire universe, and there's branches of these wave equations, basically processes that happen, and every time a measurement happens, you entangle more and more of these branches of the wave equation. This is often usually interpreted that multiple universes or realities are what you get. It gives a little bit too much. That gives a little bit too much. What's the word? A little bit too much emphasis to the human reality, I should say, would be like weird. It's a little bit weird if you want to think in just the realm of physics, but like, of course, physicists are humans, so we have to think humanistically. So it gives a lot of emphasis to what a human reality is, to say that, it's, multiple universes or multiple realities. But the kind of like the more dull, dry way of stating it is simply that, that there is a wave equation that covers the universe. There's branches of this wave equation. And when you take a measurement, branches of these waves, entangle and becomes more and more complex and more of an entangled wave equation of the universe. And then the last interpretation is Bohmian, the pilot waveguide interpretation. And that's basically just saying that there's underlying waves, mathematical waves, that guide the measurements to be a specific outcome. This is a non-local process, of course. We know that it can't be local due to Bell's experiment, but nevertheless, there is something that is guiding these probabilistic quantum equations to be something specific, where it's not probabilistic, where it is something that has some underlying thing that governs that. But Bohmian is by far the interpretation I understand the least. So if anybody does have more information on that, feel free to let me know. But around the same time as Benioff's paper, we had some other interesting papers come out. So Benioff came out again with this quantum computational paper that basically stated a way to construct a Turing machine using Schrödinger equation style logic laws. And then Benioff's paper was was followed up by a paper from Tommaso Toffoli. Of course, we know Toffoli. I actually don't know which one came first. Toffoli was February 2nd. So I wouldn't necessarily be surprised if Toffoli's paper came first. I don't exactly remember. Something to look out. But either way, Toffoli, like, there was information theory happening. People were trying to connect these quantum mechanical systems with computational gates, and Toffoli did that by producing the Toffoli gate. Of course, that's a very reversible gate, which we know by now there was reversible processes that were already being shown in the mid-70s. So Toffoli extended that into reversible computation gates. Then we have the XOR gate and the NOT gate. Both of or the XOR gate has some issues with having an analogy in computers where it's not a one-to-one analogy. There isn't a one-to-one analogy. And then, of course, the NOT gate. And so these were the gates that Toffoli came up with, which now we know are widely used across quantum computing and very, very important. Let's see. So by this time, quantum computers are known amongst informational theories for sure. And the very, very first and most famous conference is held in 1981. I think the conference was named the Physics of Computation. And the two big speakers that spoke at the very beginning and kind of like laid down the groundwork for the entire thing were both Benioff, who continued discussing his information, his work on the Schrodinger equation and the Schrodinger equation as a Turing machine, and then also Feynman, and we're going to talk about what Feynman said. And that was Feynman kind of laid down so Benioff did that, but Feynman's work was a little bit different. He basically showed that there are quantum processes that cannot be done with a classical computer. And that was big. Why was that big? Well, because that meant that we needed a quantum computer. Basically laid down the work to be like, if there is a computer process to happen here, it has to be done quantum mechanically. Why is that big in other ways? Is because, again, remember, there was still the same thing going on, that people still wanted to know about quantum consciousness. They thought that consciousness was I should stop saying quantum consciousness. It's bad blood. They want consciousness as a quantum system. Because people still thought that consciousness was a quantum system and that it could be described using quantum mechanics. So let's see. So let's read from what Richard Feynman says. This is the closing remarks to his keynote speak during this 1981 conference, the big one about this, and you will recognize one of the lines. Let's read what Richard Feynman said at the end of this talk. So I would like to see if there is some other way out. I want to emphasize or bring the question here, because the discovery of computers and the thinking about computers has turned out to be extremely useful in many branches of human reasoning. For instance, we never really understood how lousy our understanding of languages was, the theory of grammar and all that stuff. Classic Feynman. Until we tried to make a computer, that should be a quote right there. The theory of grammar and all that stuff, Richard Feynman. Until we tried to make a computer which would be able to understand language. We tried to learn a great deal about psychology. By trying to understand how computers work, there are interesting philosophical questions about reasoning and relationship, observation and measurement, and so on, which computers have stimulated us to think about anew, with new types of thinking. And all I was doing was hoping that the computer type of thinking would give us some new ideas, if any are really needed. I don't know. Maybe physics is absolutely okay the way it is. The program that Fredkin is always pushing about trying to find a computer simulation of physics seems to me to be an excellent program to follow out. He and I have had wonderful, intense, interminable arguments, and my argument is always that the real use of it would be with quantum mechanics, and therefore full attention and acceptance of the quantum mechanical phenomenon. The challenge of explaining quantum mechanical phenomena has to be put into the argument, and therefore these phenomena have to be understood very well in analyzing the situation. I'm not happy with the analysis that go with just the classical theory because nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. Thank you, Richard Feynman. But I mean, so memes aside, there's a lot of good things that he says in there too, right? Like there's a lot of interesting things that he says in there. And it's kind of getting to the point of like, we are going to be limited by classical computers. Remember, this is 40 years ago. 40 years ago. And they already are talking about understanding limitations of quantum computers. Because it is true. Nature isn't classical, damn it. So, yeah, it is true. It needs to... nature is quantum mechanical, and in order to understand those phenomenon, it does if we want to do it computationally, then we're going to always be limited by that fact. So my background is anthropology, cognitive archaeology, and I just can't get over the notion that the first impediment that obfuscates the inner workings of our cosmic reality is the mystery of human consciousness itself. Yeah, I think that's really, really interesting. Human consciousness is a mystery. But I think physicists are comfortable believing that it's quantum mechanical and that we need to understand the quantum mechanics at hand if we want to understand consciousness. I think it's convincing others that don't study quantum mechanics to think that way. It's going to be a huge issue. And then let's finish up the talk by talking about what's going on now. 20 years after this conference, almost 20 years after, in 1998, there is a good story, a good ending to this. The first quantum process was carried out using 2 qubits, using what's called nuclear magnetic resonance. And they used those 2 qubits to solve Deutsch's problem. I have a little excerpt here from our book. We actually had a whole talk, a whole discussion series lecture about Deutsch's problem. Let me just give you the quick and short of it. Alice in Amsterdam selects a number x from 0 to 2 to the n minus 1. Those are all of the numbers that Alice can pick from, and she chooses one and mails it in a letter to Bob in Boston. Bob calculates some function f of x and replies with the result, which is either going to be 0 or 1. Now, Bob has promised to use a function f which is one of the two kinds. Either f of x is constant for all values of x, or else f of x is balanced, meaning that it's exactly half zeros and half ones. So what does that mean? That means, so Alice's goal is to determine with certainty whether Bob has chosen a constant or balanced function corresponding with him as little as possible. How fast can she succeed? Now, in order to figure out that classically, Alice has to get 2 to the n minus 1 divided by 2 to the n minus 1 divided by 2 plus 1 letters in order to figure out if it's balanced or if it's not. Because what if Alice sends Bob, or what if Bob sends Alice every single letter back, every single number back, and then the last one, that 2 to the n minus 1 over 2 plus 1, divided, it is in fact a different outcome. I think I did my math right. Someone can correct me if I did it wrong. But what if every one of those is a 0, and then the very last one, that very plus 1 at the very end, turns out to be 1? Then they'll know if it's balanced. But until they get that plus 1, they won't know, because, that it could just be chance that every single function returns a 0 all the way up until that very last one. So this is Deutsch's problem. It turns out quantum mechanically it can be done in, I think, 1 letter. I think it can be done in 1 letter. So that's maybe 2. I can't remember. You have to watch the YouTube video. I don't remember, but I'm pretty sure it's 1. And then you can infer something about the other one. And then if you infer that, you can decide whether f of x is balanced or if it's a constant. So that's an interesting thing. And this was what was solved in 1998 with a real quantum computer. Now, again, we haven't really been able to turn Deutsch's problem into anything other than just a novel problem, an interesting problem, but nothing that has given us any insight into the world of quantum mechanics. But it was done firstly by Jones and Mosca at Oxford, but shortly after it was done by Jones and Mosca, it was done by good old Isaac Chang. So that was kind of an interesting thing I saw. In 1998, he was doing this, and then he wrote a textbook on it later, which is always kind of cool to, like, when you see someone's name in something, and then you're like, hey, I know that name, and then you find out that you've been using their textbook for, like, a long time. P versus NP would be huge, and it would also be a quantum computational problem, but it's not Deutsch's problem. Unfortunately, I don't think people, and maybe somebody, and that's just to say that we haven't been able to do it yet. Someone might be able to take Deutsch's problem and turn it into something very useful. But in the meantime, right now, Deutsch's problem is still just a novel little exercise that's kind of cool and shows the power of how of a quantum mechanical process. There's also some other things that I talk about in that video that make it a little less as exciting as it sounds. But nevertheless, it was done. It's good. It has all the properties that we want in a good quantum mechanical problem to solve with quantum computing. But yeah, nevertheless. Oh, geez, dear. Oh, man. I've been looking at my notes. I haven't even looked at the pony. Jeez, Lou, look at that. Look at that view. Real good. Okay, anyways. So that was always that's a fun lesson for me to learn. I mean, we've been using quantum computers a lot. And the idea that they had this, that the roots are so interestingly linked to people wanting to know about how quantum mechanics exists in nature. So the first thing, how does quantum mechanics exist in nature? Well, you got to write a quantum computer. Well, wait a second. It's interesting too, though, is that quantum computers are not like how you would imagine classical computers. Like classical computers started as these I don't even know how classical computers started, but these physical things that you would manipulate to carry out information transfer from one bit to another, right? That was how classical computers started. But now we do the same thing, but we do it quantum mechanically. We do it quantum mechanically, which is weird. It's still just a physical system, like an ion trapped in a laser or whatever. Some sort of particle trapped in a potential well and then released. And then, or manipulated, or done on something else. I mean, there's these physical things that we're manipulating. It's now we just think about these computers as being like these mystical things inside where you just send electricity and it carries out over like this electrical board and stuff. And it doesn't feel like it's just things turning, gears turning. But we're still in that process we're still in the gear process turning of quantum computers where it's, you need a physical thing to manipulate, to do something, to actually process the information.